Okay, good morning, everyone. A few announcements. Remember, there is a tape ahead today. If you're interested, it'll be from 11 to 12:15 in the Skilling Auditorium, which is just not too far from here, and that will be played, of course, in the live class time period next Tuesday, February 1st. On the midterm exam, just a reminder, that's February 8th, and the exact room. Last time I put the CIS auditorium, I should have put CISX auditorium. If you're not familiar with what the X means, it's the newest section of that building, which is out the part that's closest to Campus Drive. It's kind of a wing along the side of the building, and at the end of that wing on the first floor is the auditorium. It shouldn't be too hard to find if you get inside the building, but I should have put CISX auditorium for that midterm exam. And again, that one's February 8th. In terms of problem set number 4, which will be due next Thursday with no late homework, and Ed will have the solutions up on Friday. We have the following problems. 2.3, so we're in chapter 2 now, so everything will be a problem from chapter 2. 3, 5, so this does not mean problem 2, this means chapter 2 here. So problems 3, 5, 6, 10, 11, 15, and 17. And of course, as usual, feedback. Now in terms of a help session for the midterm exam, we typically have something in between when the homework solutions come back and the exam, which would be the following Tuesday. So that's in somewhere in that 3-day period. I'm going to guess sometime on Monday, but I have not been told yet as to exactly when or where that would be. But we won't have the help session on February 8th itself, because that will be kind of useless. So we'll try to move it up a couple of days that week to prepare for the midterm, but I do not have the date on that yet, and we'll announce it both on a website, of course. You can always get information there, as well as in next Thursday's lecture, which will be the next live lecture that we have. Okay, any questions or anything? Anybody have any problems, issues? Okay, today we start chapter 3, which is probably the most significant section of the 379A class, and it's going to be on inner symbol interference, which is sometimes abbreviated ISI, and we'll have kind of an intro to that as our first topic. And we're going to talk about receivers, what I call the receiver concept. We're going to try to model inner symbol interference, ISI again, and we're going to go back and pick up now, as we do this, correlated noise, which was section 1.7 in chapter 1, and these are all in 3.1 of the course syllabus and the class textbook. Okay, so let's talk about ISI. At this point, you have a pretty good idea, I hope, about modulation, in particular how it's used and analyzed on the additive white Gaussian noise channel. So if you had kind of a nice communications channel and you could characterize it by some additive noise, and you knew the signal-to-noise ratio, I would hope, especially with this week's homework, most of you be able to look at that and say, okay, signal-to-noise ratio is so much, I can get a certain data rate across this channel if my symbol rate is given to be some number. What happens, of course, in real systems is that the channel itself is some type of filter. It may be an easy filter that doesn't distort the signals too much, in which case the analysis we saw in chapter 1 and the modification of that in chapter 2 follow pretty straightforward, and you can analyze the system, evaluate how many bits per second, what probabilities of error would actually be for some kind of modem design. But being the kind of people we are, we always like to go faster, especially when you're younger, this happens. Everybody wants to go faster. In all my years in data communications, I've never seen data rates go down. They always go up with time. People want more data. They want it faster for a variety of different purposes. And what that means is they stress the communication system. So perhaps that means they're widening their symbol rate, which means they're following messages more quickly in time. The faster we send messages, the more messages we get across the system per unit time. Well, closer in time means wider in bandwidth. And so any filtering in the channel that was occurring now is becoming more significant. Typically, the wider the bandwidth, the more of the channel we see, the more likely we're going to see the edges of the channel where there may be some kind of filtering effects ongoing in the system. And so it's going to get harder to distinguish those messages going through the system. And that is really the domain of inter-symbol interference. If you think about this acronym ISI, inter-symbol interference, the very name itself is telling you what is happening is that the symbols are starting to overlap with one another, at least as far as the output of the channel is concerned, and so they create noise, interference, into one another. So let us suppose that we send a one-dimensional message, and it could be a complex message. One complex dimension is really two real dimensions, so that would mean we're sending QAM in that situation based on what we saw in Chapter 2. Successive messages. All right, sounds like a good idea. We don't want to use our communication system just once typically. We'd like to send successive messages. And so what we're going to do is on our inputs, it's basically one-dimensional. I'm going to drop this subscript little n. Okay, remember we used to have in our modulator a subscript n that went from 1 up to capital N. Okay, since everything is one-dimensional, even if it's complex, we'll model the two real dimensions as a single quantity, so I don't need to keep that index any longer for the number of basis functions, because there's only one basis function in effect. It may be a complex basis function for QAM. So I'm going to replace n by k, which would be a time index. So k is now going to refer to the point in time or the symbol period in which I sent the message. And by adding that index, of course, I'm implying that we're going to send more than one message through a transmission system. And of course, we still have that basis function. Let's call it 5t, even if it winds up being complex in some form or another. That's our basis function, so I'll just put bfunc, basis function, underneath that. That then in turn passes through some filtering in the channel that may become significant, especially as we try to transmit faster and faster. And that is the channel impulse response. Before we get to the point, which is typically close to the receiver, where noise gets added in the front end of the receiver, as it would have to be in all practical systems, often that's additive white Gaussian noise. And we're going to call the output of this system, I'm going to change the output just slightly. Instead of calling it y of t as I did earlier, I'm going to put a little subscript of p on it. I'm going to reserve y of t for something we're going to talk about momentarily. This cascade of the basis function and the channel filtering is often called the pulse response. Not the impulse response, but the pulse response of the channel. The pulse response, why we call it that name, well, it's the impulse response of the channel here convolved with some pulse shape or some basis function. Sometimes we call basis functions pulse shapes. So it's the pulse response of the channel. And we call it P of t, P of course for pulse response. Okay. And what happens is with successive transmission, my output of the channel, if I were to just look at the signal part, which I'll call x sub p of t, forget about the noise momentarily. We kind of know what to do with noise anyway. We've been studying it for several weeks. So let's look at this inter-symbol interference effect, which essentially arises because I'm going to sum at the output, it's a linear channel, the contributions from each of many messages over some interval that it contains many symbol periods. And for each of those symbol periods, I have the message itself, or the symbol that corresponds to that message, which is one-dimensional, real or complex, x sub k, times the pulse response, of course, delayed by the time at which the message was actually sent into the channel. So we could think of this input here as basically being x sub k delta of t minus kt if you want, and convolve that at each point in time and add them together as they pass through the channel. Really what happens is we get x of k times phi of t convolved with h of t, but that gives us the same expression, okay, for the output of the channel without any noise. And so what is happening here is that message x0 is providing an output xp of t, and message x1 is providing an output p of t minus t, and so on. X2 would provide x2 p of t minus 2t. And the output is the sum of all these essentially modulated pulse shapes that are coming out of the channel. Now, if we were really fortunate and h of t were a delta function, so there weren't any distortion, and we designed the phi of t so there wasn't much overlap between the messages, then these output would not overlap either, and so we'd be able to continue with the same type of detector we saw in chapters 1 and 2, sometimes called a symbol by symbol detector. We just make a decision for each output. But if they're overlapping, we're starting to get distortion between the different messages. So what should we do in that case? Well, of course, it's going to depend on the amount of overlap that we have. And when we get into intersymbol interference, we're going to be concerned, as is often the case in practice, where there's very significant overlap between the messages. And so what we might see, for instance, is a message transmitted at time 0 that has a response. System doesn't necessarily have to be causal. I could define time 0 to be just about anywhere. So my pulse shape could start before time 0, could come after time 0. But let's suppose that actually is the case. So if I were to go back in time, forward in time, various units of the symbol period, I might see a waveform perhaps that looks a little like this, perhaps then kind of decaying gradually to 0. So that's what came out of the channel for message x0. Now, of course, it's going to depend on whether x0 was plus or minus 1 or plus or minus 3, or if it's a complex number, it would have a real and imaginary part somehow multiplying. I could have a second little graph for the imaginary part if I wanted to, if it was complex. But this waveform is x0 p of t. Now, let's suppose that x1, when it's transmitted, is actually negative, and maybe it's a little higher in terms of its amplitude. So what will happen is I have to delay this because it's been transmitted later in time, and I have opposite amplitude, so I'll try to draw the curve in here, and pardon my my graphical skills are not real good, but you get the basic idea that I'm trying to take this waveform, invert it, and make it a little larger as I'm drawing here, and hopefully I do this reasonably well here, and we get something like that happening in the system. Now, what's going to happen is these two being added together. What happens here is at time 0, this second shape, which is x1 p of t minus t, could add kind of a pretty big negative contribution in and around time 0 here when I'm sending the first message. So the interpolated version, or the sum of these two waveforms, may not look that great. It may look kind of something like this region where perhaps the intersymbol interference from the second transmitted message is so great that it pulls down the amplitude of the first message, and it'd be really easy to make an error in my symbol by symbol detector. because I've essentially lost all of my signal at that point. Okay, so the and to give you well, I have a few plots of this coming later, but we'll hold off for now. You get the basic idea that these things can interfere with one another. So what are potential solutions to this? Well, I would suggest that you all actually know exactly what to do, what the optimum thing to do is, and it's essentially what you were taught in Chapter 1, except that you would block off your messages into groups of, let's say, capital K messages, and call that one big giant super symbol. Now, if I happen to have M messages at each point in time, I would have M to the K possible messages over that symbol grid. So there's a lot of them there. If I did these super symbols every so often the channel, maybe I have a little bit of gap, so I don't have to worry about intersymbol interference in that gap. When I send these big blocks like this, that percentage I'm losing there is pretty small on the edge of the block, so I could throw that away. Okay, as long as I'm crunching everyone together for 95% or 99% of the time. And then I could design an optimal receiver for this situation. I have to go do Gram-Schmidt, remember that from the back of Chapter 1, on the signals, get a set of orthogonal basis functions, set up my optimum detector, and proceed. And I would indeed get the best possible performance, the minimum probability of a symbol message error. And symbol is now this supersized symbol. But the probability of deciding the wrong sequence of symbols here would be minimized if I did that. But that, unfortunately, sounds kind of complex, and in fact, it is pretty complex to do that. So we're going to run out of MIPS somewhere, or run out of resource in a receiver to be able to implement that massive type of search over K dimensions, M to the K symbols, try to find the closest one. Could get pretty nasty. And the P of T, obviously, the pulse response itself would affect the complexity of that system. We'd have new basis functions we'd have to figure out. They'd be a function of the channel to actually do that. So that's a fairly complicated endeavor to try to consider that. And I'm not going to try to consider it in the E379A. We will come back to it and simplify it in 379C if you take that course. But the typical solution, unless we get to the most sophisticated types of transmission systems, is to use the symbol by symbol detector. Anyway, they just can't afford that complexity, so they take whatever performance hit they get. This is not optimum. It's suboptimum. And there is a loss. It's not as good as doing what I just described. Okay, but maybe the loss is not so small. Or maybe I can do something to keep the loss within some reasonable bound, and that gives me a much cheaper receiver than it would take to actually block everything off into packets like this. So that is one potential solution. There is another solution that is really the subject of the C class, which is kind of interesting too, and used increasingly in transmission systems today, and you would recognize it from somewhat of a simplistic viewpoint of Parseval's theorem as going into the frequency domain. Let's say our channel looks like this, P of F or H of F even, looks something like this, where this is frequency. And what I would do was I would send a bunch of QAM signals all tightly packed together in a channel, and I would make these things so narrow that that channel basically looks flat, okay, in this region right here. You do that, channel's flat, impulse response is a delta function. No intersymbol interference on any of these tiny little subchannels. So that's the third approach that you can take to this type of design. Now, it turns out with this type of approach, you can approach the optimum that you see up here in terms of performance. But with the symbol by symbol approach, which is often the easier approach to take, you cannot often get to that ultimate example. So let me give you a few examples of situations where we might be forced to have to deal with intersymbol interference. Yes, sir.
Sir, having the channel response, can we design it in such a way to have, for example, a sink as being the PT? Can't we design our base function in order to have...
Well, you can design a set of basis functions to do that. If you were to take a single basis function, your intuition is good, except in the way that you're headed in trying to solve the problem, you would have to consider the transmit power. Okay, and if you had a channel